Welcome to Time to Talk Quantum. I'm Dr. Kris Naudts, neuroscientist and psychiatrist, founder of Culture Trip and co-founder of Firgun Ventures. Today I'm joined by Yariv Adan, founding general partner at Ellipsis, an early-stage AI deep tech VC focused exclusively on transformative AI solutions. Previously, Yariv spent 17 years building AI at Google, rising to senior director of product management. He co-founded Google Assistant and Google Lens, and led Google's Cloud's conversational AI and applied Gen AI teams. I'm also joined by Dr. Robert Sutor, founder and chief executive of Sutor Group Intelligence and Advisory. Dr. Sutor is a theoretical mathematician by training and spent nearly 4 decades at IBM, where he played a key role in leading the company's quantum efforts. He serves as a non-executive director at New Quantum and is also an adjunct professor at the University of Buffalo. Dr. Sutor is the author of Dancing with Qubits and a popular quantum, tech, investments and applications newsletter. It's time to talk quantum. Okay, so we're going to start with talking about AI and then take the conversation towards quantum and indeed the synergies between the two. Talking about AI, of course, means talking about NVIDIA and Jens Huang. He talks about AI not as a single technology, but as a 5-layer cake. One with the power and the energy, then the chips and the computing infrastructure, the cloud and data centers, the models, and of course the application layer. And all of those, he says, need to be built and operated. Now, Yariv, you were at Google for just under 2 decades, I think. How did Google think about this 5-layer cake?
I think it was different, a bit different time. I think that the last 2 to 3 years changed a lot. I think Google kind of agreed and was operating at all of them. I think, definitely, I think I think first Google is the only company in the world that actually operates across all the stack, right? And have all the components. From the data center to the CPUs, actually, solving energy, the cloud, and then applications that are used by billions of people, right? They're the only company on the planet within the AI, including frontier AI models. So it's a very interesting, unfair position to be in. And I think that intentionally they actually built it in that way and are now profiting from it. I think the biggest change that has happened, and to me the interesting conversation, is one, what happened to the application layer, because it used to be the case that it was very hard to build and to distribute the application layer, and this is why you had kind of companies that specialized in that. And also, there was a very clear separation between the application layer and the compute or the cloud layer. So having it or not having it, or the resources related to it were not that important. And I think what the large language models are doing are completely changing the relationships and the dependencies between these layers. I think on the one thing what they're doing, they are commoditizing the application layer to a large degree. Because one, you have this whole new class of application that you never need to buy. I call it ephemeral applications, where you basically prompt a product. You're basically saying, oh, I need to do this and this and that. And you're basically building a one-time product for one use case, for one user kind of on the fly, and you throw it away. And the cost of it is like the cost of a napkin when you drink coffee, and you don't save the napkin for the next time you drink coffee. And that actually, kind of a new commoditizing competition. On the other hand, the speed of building application, you need many less resources, much less time, and much less people. So many more companies can do it. And then just the numbers don't work anymore, right? Actually, when you have 2 orders of magnitude more companies building the same application, it's very hard to have a winner get all. It's very hard to have the numbers that VC need on a hit and miss basis. So that again, create commoditization. The third part, because it's so easy kind of to build application, the big players that own the user, whether that's frontier models or hyperscalers, can also go vertically much more than they used to. And they already have the distribution. So that creates another problem. And then, even writing code, because these things can write code, writing code is much faster and so forth, that also. So I think on one hand, there is much more pressure on the application layer. And if in the past it used to be the place where you have most margin and stickiness, I think that goes away when the model takes a big part of that. So I think that's one interesting thing that changed. The other thing that changed is that, okay, so the key game is in these models. However, I think there is two things that dominate the economy of models. One is how much compute you will have, because that's your ability to answer the demand. And it's a big bet, because building data centers or renting, it's $1 billion businesses. And a company, even like Anthropic, that raised billions of dollars, or Young Lacoons or OpenAI, if they are wrong by a year on the demand in 2 years, they go bankrupt. So they need always to kind of underinvest in compute, although they know demand might be higher because they cannot afford missing the prediction. The other thing, when you develop a model, it's always, once you buy the compute, it's always a trade-off on how much do you put in training and research and how much you put in inference. Training and research goes to cost. Inference goes to profit. If you need to raise money and you are not profitable, you need to actually do less on the investment and you need to put some resources on the inference. So basically you are moving slower in a field that is moving very, very fast. So now take the step back and think about Google, that already has everything, that can outspend in the billions, that doesn't care about inference revenue because it doesn't need it. I think that creates a very challenging position for any players that don't have the existing assets and don't have the deep pockets to play this spending game for multiple years. So to me, yes, that thing always existed, but the relations and the games and the profit and the value and differentiation and differentiability is very different. And I think the differentiability is all in the compute and the ability to do it at scale. And there is 5 companies that can do that on the world. One company that has the entire stack. Second company that is NVIDIA, that has good parts of it. I think Microsoft and Amazon are not in a great point. And everyone else, I think, is just missing very, very critical pieces. And you see OpenAI that were trying to raise, hundreds of billions to build this capability, and are discovering that it's not that easy to do. So yeah, that's some opinions.
And to be clear, Jensen just gave a very friendly description regarding a birthday cake, right? This idea of a software and hardware stack goes back at least to the 1960s, right? And it's embedded in telecommunications, right? From the physical layers all the way on up. So this is common. Even if we don't talk about AI, and you are talking about computers, you've got electricity down there at the bottom, right? So, the idea of layering makes a tremendous amount of sense. In fact, if you were to Google, hardware and software stack, you'd probably get several hundred different pictures of the stack with different elements to it. So a lot of that's common. I think what's significant for what he said was that he directed it toward AI. But even once you get in that, there are sub birthday cakes in each layer. There are layers, right, and things like this. So he was expressing it, I think, in his modern terms for the products that NVIDIA offers, whereas it's extremely general computer engineering concept.
But it's a very good framework for people to understand what's at stake, I believe. And it allows, indeed, like Yariv said, to explain these moving layers and how they are differently approached across these hyperscalers. Now, do you think, Yariv, that some of the companies is getting it very wrong in both the application layer and in big tech? And will some indeed, as a consequence, fall away or fall behind?
Yes, I think companies are getting it wrong in multiple places. I think the biggest place where I think companies and investors are getting it wrong is in the application layer. I think the rules are fundamentally changing. And if to be a little bit in the spirit of this podcast, I think we moved from classical physics to quantum physics, and we're just struggling with the implications of that. I think what used to, The only thing that stays the same is that in order to have a good, high margin, sustainable business, you need to have some defensible moats. Or otherwise you are in a commodity and you compete on price and margins go down, and it's a very different business in different ways. What counts as a moat, I think, is completely rewritten. Like I said, because it's much more competitive, the numbers are different. Generating code is not a mode. Being first isn't as important where the timelines are shrinking. I think the ways that we're buying software are going to change. Today, procurement is done by human, based on human trust and human criteria. I think that very soon we'll see agents buying software, much more transactional than long term. And an agent doesn't need to trust the agent. It needs to trust what the agent can do, and an agent can prove what it can do, given an eval or an LLM as a judge. So a lot of these modes, I think marketplaces that are not inherent to products, but are inherent to humans' limitation handling period-to-period scale. But agents can do period-to-period at super scale. So that goes away. So I think a lot of the rules that used to govern venture and startups and defensibility are just being rewritten, and I think people are slow to accept that. The other part where I think companies and investors might be getting it wrong is what I said, that at the end, if you look at the long-term game of these foundational models, it's an economic game, and it's a very expensive one, and I don't see how you compete with some of these, of these companies that can outspend, but also have all the infrastructure and all the skills and everything that is required. And I think that's so when I look at Jan LeCun or others, I'm like, it's like winning the Olympic Games day after day for 4 years against the best sports people on the planet, right? They need to consistently do that, not just for 1 year, not just for 2 years, to actually return the investment. So I think that's something that a lot of people are overlooking.
I think so computing is extremely heterogeneous in terms of the components, right? We can talk about GPUs, maybe they're from NVIDIA, but who makes those? Where do the supplies come from? You talk about the racks, the physical computer racks, right? Somebody makes the little screws that go in this. So as much as NVIDIA or anybody else might want to own the stack, right? They can't, they're not going to make the little screws that hold the things in here. Same way with making airplanes, a Boeing or an Airbus, right? I mean, they do the overall design, but they subcontract to it. So startups need to figure out where they play in this heterogeneous collection of components, right? They are suppliers to do what? Now, some of them will survive because they're essential. They do what they do better than anybody else, or for whatever the reason may be. And others may just be gobbled up in different ways, or be made to survive. So NVIDIA invested $2 billion in Coherent last week, right? Which is a photonics company. Gee, photonics, lasers, what's NVIDIA doing with that? Well, photonic networking is going to be a huge part of data centers and things like that. So they're not buying Coherent, at least not yet, but they're ensuring their survival, right, to fit into this. So it's very complicated how to do this. I will also say that in the past, consumers, users have objected to having monolithic stacks owned by single vendors, the operating systems, the applications, and things like this. A lot of open source got started for exactly that same reason, saying, we don't want this vendor to own the operating system. We need Linux, right, and things like this. So wherever we are at this time, and the moves you're seeing today can change over time as people, investors, and so forth, change their attitudes about how these stacks are built.
Do you see differences in those patterns that you describe, Yariv, outside of the US? Is it different in Europe? Is it different in Asia? Are the rules being rewritten?
I think the rules apply everywhere. I think this rule of what I call commoditized magic, where you have technology that is magic in the sense that it does things that we considered impossible 2 years before, but it's completely commoditized. I think that's almost like a nature law now. I think in Europe we're more blind to it. I think when you are in the valley, you actually see the numbers. I think you see the energy. I think here we are a bit isolated maybe. So if you are not like really following closely, you might miss it and realize it may be a bit too late. But I don't, and also like, the big companies in Europe are actually the more, conservative ones, from the early SaaS or even before, right? Which again, going to dissonance cognitive, this is like where the mindset is. So these are like the loudest voices. So I don't think it's different. I think we might be a bit behind and we might be missing how fast and how much is happening.
How do you think about China?
China certainly is looking to do as much of it themselves as they can, right? So in that regard, and that brings up the notion of not just, if you will, corporate control, it's sovereign issues, right? So when a country or a region says, we need to own this, and as we've seen, sometimes geopolitical issues can come into this, right? You see this in France in the quantum industry, right? They are very, we will have one company for every type of modality for quantum. We will support them. We will make sure they survive. They mention the EU, yeah, occasionally, but sometimes it's like France in the EU, Germany in the EU, Finland in the EU, right? Note which one comes first, right? So it's a little bit more difficult to do it on the regional level, but it does happen. And I think people are trying to figure out how to make it work now. It's ways they haven't necessarily done it before, they're now thinking maybe they should, right? So there are some unknowns there.
Yeah, I think technology, AI, quantum have certainly turned sovereign and geopolitical. We hear a lot about it in the news. This is not a show about geopolitics, but it's worth commenting, I think, on what's happening in the Gulf. Does that lead to a rethink of data center distribution? I don't know if you have any thoughts on that, Yariv or Bob.
I think the world is unpredictable. Right, like I looked like 10 years ever since, or even before that. I remember in 2007 or 8, the biggest worry was $200 for a barrel in oil, and then subprime happened, and then ISIS and immigrants, and COVID, and then the Arab Spring, and now this Iran war and Ukraine. I think that trying to predict the instability and in which region and where it will happen is a tricky thing. Again, I think the regime in the US and what's happening there is also a lot of instability, and US and Europe suddenly creates new geopolitical. So I don't know if necessarily the Gulf is a long-term risk. Necessarily, I think actually, these countries have a lot of money. They're super investing, super smart. Usually stable. So. But again, not my expertise.
Yeah, not. So, all the things you mentioned, there's so many variables, and they're all connected to each other. See, that's the thing. They're not all independent variables, right? Something happens this, and it affects this, and so forth, and I'll certainly say that it makes investing tricky. Right? Where does the money go? To whom? Where are they located? To whom are they going to work? How can they grow if all these other things are happening? Things like that. So it's none of this instability is helping. That's a brilliantly deep statement, but there seems to be a lot more of it now than usual.
Yes.
By the way, Israel is an interesting microcosmos to look at, right? Israel was such an important hub for VCs and others. And then there was I would call it now the first war, right? October 2024. I was surprised how quickly a lot of VCs backed away and didn't want to do anything with Israel, even ones that operated, because actually things didn't slow down. Yeah, for sure there is a lot of risk. Now maybe customers will not want to buy Israeli stuff. Maybe they cannot travel. But the key thing about founders being able to build great companies very, very quickly didn't change, and people did it while, this emergency room. I was also surprised how quickly afterwards many came back. And now again, there is another war. So I found that at least on the investment side, in the VC world, there is a very overreaction in the short term and very short term memory afterwards. I don't know how that applies to data centers. I've never built a data center myself, so I don't know if people are looking at it versus other stuff. But yeah, I guess we'll find out.
But regardless even of data centers, I mean, AI is a dual-use technology, just like quantum is. How do you approach that in your VC firm? Dual-use technology, you're happy to invest in it. What is the position?
So, well, like to your point, right? Like everyone is now also a defense company if they can. So we do not invest in anything that we think can be even remotely close to offense. We're fine on defense, although it's not an area of focus for us. But we have seen some great companies, but we said no, we do not want to support technology that can harm people or basically. Yeah. So I like the do no evil. I like, being proud of products that I supported and that I can point at the value that they generate. And I don't want to, nothing, at least in my opinion, is worth regretting what you invest in. So yeah, the short answer, no to anything that is close to offense.
And if we want to talk geopolitics, I mean, we don't need to talk about Anthropic again. I think it's all over the news. People have read what there is to read about it. But a lot of people ask us, and this applies to quantum and AI, I think, what happens if indeed there is a Taiwan-China conflict? And if that were to happen in the next 1 to 2 years, which a lot of people believe might be the case, we don't have that much time. And what should we be doing in these next 12 to 24 months to indeed avoid lasting consequences?
Hard to speculate on such an event. I think, I can say about China, right? Like China is definitely maturing to being, I don't know how to call it, the technology superpower. I visited last year in Shenzhen, in Shenzhen and in Shanghai, and I met both top companies, or also the Tencents and the Alibabas, but a lot of robotic companies, a lot of the startups, the Kimis and the ones that are building frontier. And then I also met all the top VCs, and they are at the forefront. They are like aiming to be the global leaders in their domain. And of course, in AI, you see it. Definitely on the model side, they chose to be kind of the open models of all things. They are actually, leading, and they're very close to the closed models. So I think where China is and where China will be, in my opinion, at this point, is mostly in Chinese hands. I think the VCs over there are outstanding. A lot of their LPs are actually from the West. All of them have both Chinese and USD funds. They are innovating at the forefront of robotics, of semiconductors, now also of biotech, self-driving cars. So, yeah, I think that ship has sailed, in my opinion.
On the quantum side, I mean, you can always bring China in. The fundamental problem is it's very hard to verify what is being said, right? And honestly, this is true for a lot of companies around the world, right? I really wish, for example, the media would say so-and-so claims this as opposed to so-and-so did this, because all they're doing is reading the press release, right? So it's very hard to interpret, by the language. But moving beyond China, at different times I've seen things like Australia, the world leader in quantum computing, the UK, the world leader in quantum computing, repeat for France, repeat for Germany, repeat for Canada, so everybody is kind of vying for at least marketing dominance, if you will, if not actual technical dominance. And this is to attract, investment. It's to sometimes they're telling it to themselves so that they actually do, sovereign wealth funds and things like this to get the right people in the country to get behind what they're trying to support.
And then we blame large models for hallucinating. Yeah, people hallucinate all the time. Yeah.
I had a call with an investor yesterday. Yeah, and they were talking about how they used AI and how beautifully it puts it all together and everything. And then they edit it and they fix it. So right?
No, but there is the general question on the race and the competition, and a lot can be said about that. If there was indeed a trade war turning into an actual war and you have a blockade of Taiwan, then certainly that would have consequences. That's not speculative. That would be consequential. If TSMC could not export its chips, then Nvidia would have a problem. Other tech companies too. And is the fear of speculation not also a form of denial to address some of these issues that are perhaps inevitable?
Well, it's not, again, it's not just Asia. I mean, with what's happening in the Middle East right now, we talked earlier about the price of oil going up and things like that. Huge issue. Affects transportation, right? It affects everything. Transportation-wise, somebody was telling me basically to get from Europe, let's say to Singapore, there's a 100-kilometer wide corridor you can fly in because of closed airspaces and things like this. So, yeah, we can talk about China and talk Taiwan, but the rest of the world has also major issues about disruptions to any of these sorts of things. Mm. So we want to get back to Jensen's electricity. We want to talk about fuel and things like this. There are a lot of disruptions that occur at the very lowest level of the stack regarding, perhaps not electricity, but basic materials, right? Supply chains and things like this. And those things come from everywhere.
I think to take a step back, right? Like I think it's very interesting. On the one hand, the world is very geo-connected, so events impact in a big way. And on the other, certain things are extremely concentrated. Right? There is 3 cloud providers, and one or two are actually rising. There is one NVIDIA, one TSMC, and there is a few areas where energy is generated, right? So I think the world is fragile. This is when we see that a single point of failure, whether it's this new president or a virus or something like that, actually has big turmoil. I think then the question is, does that impact also the longer term? I think that's the big question for me, or it is kind of fluctuations where things are going. That's
Yeah, I would agree with that. And it's very difficult to predict if we're looking at temporary aberrations geopolitically, or whether indeed these are permanent changes that might even get worse. It's difficult to say. If we go back a bit to VC investing in AI, Yariv, 2025 was a huge year for global VC investment in AI. I think about 100 billion or so was deployed worldwide, which is an insane number. I mean, that you almost don't hear anymore, but it is insane. In quantum, that number was 5 billion or so, give or take. So the difference is obviously there. Now, in your firm in particular,
if you look at the spend of big tech on what they spent on AI, it was in the hundreds of billions, right?
Yeah.
So it's interesting.
Yeah, this is VC investing.
Yeah. No, but I'm saying that actually that concentrated investment, and just just want to say something. In the past, when Google or whatever company invested 100, 200, 300, 300 billion, it was spread across, tens or dozens or hundreds of models in different products. Now it's concentrated on a single Gemini, on a single Claude, on a single OpenAI, right? ChatGPT, right? This is super interesting, and I think this is the key thing that is driving this key progress, right? The numbers are crazy, and the concentration is unheard of.
Yeah, exactly.
Again, I think the numbers are always telling the story, right? There is a lot of words, but you should always look at the numbers, in my opinion.
It's true.
And by the way, the quantum companies are trying their darndest to get some of that AI money.
Yeah.
Yeah, everyone is spraying AI.
I think we're going to talk. Let's not talk about quantum. Let's talk about quantum and AI, right? Give us some of that.
Yes. As a VC firm, Yariv, what can you do as a new VC firm in AI with this overcapitalization of the space in general?
Like everything else, right? You should have a product that is differentiated and be have very clear conviction of what you want to do and why. I think if you're trying to be a me too in such a world, you have zero chance. So when we created, we identified a kind of a gap in the market. So we were looking and said, okay, there is the European market. So this is we're mostly focused. We have amazing network in Israel and the US, and we're opportunistically taking deals, but not trying to compete over there. And in the European market, there aren't many VCs with our profile of real AI experts, entrepreneurs, and operators that have been operated in the field for so many, and definitely don't have our network. And we went on very early stage and very founder focused and very hands-on. So we are super involved, and every quarterly report from any enterprise, like, oh, okay, thank you, Ellipsis, for the amazing introductions and stuff like that. We put the work. So we basically found a niche, just like any startup. And now we're like expanding and building organization and building campus scouts and building an accelerator. The other thing that we did is we're actually AI native. We are 2 GPs. We don't have juniors. We don't have admin staff. From day one, we have AI agents. I used to be proud of that because we used actually to code them 2 years ago. Now it's like prompting. But actually, it means that our entire organization is built like based on AI from first principles, how we handle data, how we make decisions and everything. It allows us actually to be much more efficient, in my opinion, than many others, definitely in our size. So yeah, it's a little bit like startup, right? And we also have very clear conviction from day one about this commoditized magic. 2 years ago, people thought I was crazy. People told me this is like next world prediction. What are you talking about, commodity? I said, no. It's going to write code. It's going to do all of these things. And we started with, okay, the only defensibility is data and very proprietary data and so forth. So we were also targeting very specific companies and did not follow the hype. And founders like it. I'm pretty sure that you guys in Quantum, founders are so hungry for an investor that understands what they are doing, that can actually challenge them and can help them. And then they speak, and that brand goes on. So yeah, so really have conviction on what your product does, a very clear positioning of it, target that market and be true to it. And I think good things happen.
Yeah, excellent. Very recognizable. Do you mostly invest in agentic AI?
I think all AI now is but no, right? Like, so basically the way we're saying again is AI unlocks stuff. Like, where I'm saying, let's not automate the past, let's unlock the future. If I look backwards, every time new technology came, it wasn't about doing things better. The ones that really became big were ones that doing something completely new. The Googles, the Amazons, these guys really, did something new. So we're looking for either companies that are now solving problems that are very big, used to be very hard, and there is a very strong why now, and there is a very strong data as well as data flywheel and expertise mode. So that's like one thing we do. The other thing we're looking for is this new stack is being built, mostly by big tech, but what Bob said, right? There are companies that are actually going to build the screws or whatever that requires different focus, different expertise. Then we're looking for these ones that are either AI scale unlockers or they are so disruptive that no one actually is going to build it. And then we're really looking for the best teams in the world building that. And then so we know what we're looking for. We have a very clear, hey, do you have a data moat or you don't have? That's like, kind of a hard thing to do, but easy thing to see. So yeah, that's our focus. And then we are completely geographically and industry agnostic. We invested in biotech, we invested in robotics, we invested in AI infra, we invested in some foundation models, in manufacturing automation. Yeah, I think the future is agentic in the sense that you want people less and less to describe the how and more like, what and why, and just let the thing loop and optimize. But I try to be not religious on these kind of things. We do not do quantum though. We just don't understand, and we try to keep to what we understand.
You come across it?
Yes. And it's very tempting because it's like super smart people, super exciting space. But I think like you really need to understand it, right? Like especially the timelines and the big tech involvement. It's like it's so easy to do mistakes there if you don't know what you're doing.
Yes.
The timeline is just so critical, and people do everything they can to pull that in, right? There's an old joke that basically says quantum computing is 10 years away, right? And the people use that for decades, but it's better. Now it's 3 to 5 years away, so we must be making progress, right?
But maybe the years are longer.
Yeah, that's right.
We'll come back to that, Bob. Yariv, can you comment just briefly on world models and what your view is on it? Why this is special? Why can Yann LeCun raise 1 billion in seed funding?
Yeah, I think that has nothing to do with world models, to be honest. But yeah, if people have 1 billion, they're happy to spend it, good for them. I think it's a no-brainer to do world models. I think Yann LeCun is a little bit going into an open door. I don't think anyone thinks that everything can be solved and understood by large language model. And when you look at the stacks, they're not, they have additional stuff. I think everyone was surprised on how much can you actually squeeze and get from that pre-training layer of only text. But on top of it, they're already now, Google is training actually multimodalities. And of course, they're not training on the pixel or whatnot. They're looking at the vector space. There is, RL on top of it. And again, the RL is less about training and more about focusing the model, what it already learned. But others, Google has a very scalable world model. The Genie model is a near real time. So actually, you can actually very quickly, very soon, I'm pretty sure that they will use it as a learning loop itself. So I think it's like almost no-brainer that, text encapsulates a lot of information, but you want to learn from so many other modalities and wavelength spaces. I think we hardly touched it. I do think that we need to be careful between also confusing what a learning thing does and then what it's capable, because reducing models to say, all they do is auto-regression and text is like saying, what can you do? You're just a cell that is trying to consume sugar. Because that's kind of the learning thing. I don't know. But as you are creating something that have agentic capabilities and is really trying to deal with the world in order to consume sugar, it happens that it just learns a lot of stuff on the way. And people are connecting these models to tools and to other capabilities. Also, I personally, and maybe I will regret this because this is going to be recorded. When I look at people, we're not that much smarter than monkeys, or even much simpler animals. It's not about a very different biology or different way of learning. I think the way that humanity created our abilities is our ability to break down problems, to use tools and techniques to solve these problems and create new tools and techniques, and then we compound that. We compound knowledge, we compound techniques, and then somehow as a society, not even as humans, we manage to build this amazing set of capabilities to solve ever more complex problems. I always expected that the same thing will happen with these models, that it will not necessarily be, breakthroughs in how they learn, how they represent. I actually think that the more we train them how to break problems, how to reason, and how to use tools, they will actually be able to grow much, much faster, even if they don't learn new ways. And we see that happening. So I actually think that, we're just at the beginning of how these things actually use the tools, and the tools are still mostly digital, right? They didn't even got into the world. So yes, to answer your question, definitely world models, definitely get out from the 2D to the 3D, definitely get out from the world, although we got out a long time ago, into additional information. But I think there is also much more, and it's happening, and it's happening very quickly. Yeah, so.
Okay.
Yeah, I wouldn't invest $1 billion in that, but.
I think it's time to talk a bit more about quantum now. So Bob, I'm going to turn to you, and I would like to start with bringing it back to our 5-layer cake. Is that a different cake in quantum? Is that a bigger cake? AI people can only count in trillions, it seems. We still count in billions in quantum. But what is that cake? What does it look like?
Well, first of all, let me say just computation, whatever it is, right? Jensen mentioned electricity. Okay, we can put that down there. But at some point, there's the hardware at the bottom, and there's the applications at the top. And it's what you put in the middle. The other thing is that quantum doesn't just exist by itself, right? Quantum works with classical computing. So how do you control what a quantum computing does? That's classical computing. So whatever you might think of the stack, you need to start with the classical computing stack and understand how quantum intersects with that. right? So it's not that pure. It's basically very, very similar. The elements of, well, let's just say the programming model is completely different. Even if we're speaking of one of the models, the so-called digital quantum computing paradigm. It's probably the most similar, except it's radically different. Here's an example. You can't copy information in the quantum model. So if I were to create somehow a quantum database, and I say, oh, that has some interesting information, let me pull it out of the database, pull something interesting. In so doing, you destroy the copy in the database. So, well, that's a little dangerous, right? And then it goes on, right? There are other differences. The tools, the underlying concepts are very different. And so this affects how you actually create the different parts of the quantum stack, from the hardware to how you program them and so forth. Within the hardware, even, there are 9 different ways, so-called modalities of building a quantum computer. So IBM and Google do superconducting. Inflection does neutral atoms. IonQ, Quantinuum does trapped ions, right? So 9 of them. Very, very different about how you do it. It goes well beyond the similarity in semiconductor approaches in classical computing. So that very much affects, even if I were to write a quantum program, a quantum circuit, how we lay it out in the hardware. There are advantages and disadvantages to each of them. So at the top level, the stack looks very similar, but as you go into it, it's completely different at each layer.
Can you talk a bit more about data centers and the state of quantum in regards to that?
Well, the first thing to note is that today's quantum computers are very small. And so when I'm not being quite so polite, I might even call them toy computers, right? That is, they do not yet fulfill all the great big promises that people have talked about with quantum computers. And so the first question is, why am I putting this little quantum computer in a data center? Most of the quantum computers being used are being used for research right now. Yes, there are many that are accessible over the cloud through AWS, IBM, so forth, things like this. But that's convenience, and that's cloud access. They are not at the moment fully functional for practical applications, let's say, combining high-performance computing and quantum. People are exploring that. People like Oak Ridge National Laboratory in the US, different companies. Because you don't have to wait until you have a big quantum computer. You can say, fundamentally, how do you do this? How would we do this? How would we connect it hardware-wise? How would we orchestrate applications, parts of applications, across the different types of processors? So people are doing it. They're thinking about power requirements. They're thinking about footprint. Some of the types of quantum computers we talk about, you might say, well, okay, this is a pretty big room. we can put a quantum computer in here. Other types of the modalities, you say, well, yeah, we've got 2 football fields. We'll build a single quantum computer that takes up 2 football fields, right? Well, where's the data center fit in that, right? Is it next door? Is it in the middle? I don't know. So it's an interesting situation. It's more research right now. We certainly understand that classical and high-performance computing and quantum will work together, but the lead is very much HPC, classical, plus quantum, and that's where the research is.
Okay. What are the energy needs of a quantum computer versus a supercomputer?
Well, we don't know, honestly. There are studies trying to figure out how to do that. In particular, people try to compare it to classical usage, right? So say, well, okay, this is how much energy it takes to solve the problem classically. This is how much to do it with a quantum computer. Okay, except that you can already solve it classically. Why are you using a quantum computer, right? It's not one of these problems where, oh, it takes 1 million years, right? Classically, and it takes a week to do it on a quantum computer. We don't know how much energy, nor would we even bother with saying how much would it use in 1 million years, right? And things like this. There are studies. There's some interesting studies in France. People are trying to extrapolate on these things. In the small systems today that we have, they're particularly superconducting neutral atom science. It's not very much energy. I mean, it's small, but they're small problems. But I saw an infographic, right? So these companies, these modalities that will take 2 football fields. I don't know if it was a mistake, but when they put the little part of the infographic about energy, they included a nuclear power plant, right? Now, we certainly know about that, right, with AI, right? Seeing what's happening with Google and others buying up these little things. So it's very hard to tell, but I do think it's important to remember we're only going to use quantum in situations where we just can't do it classically. Either it would take too much time, right? Too much memory, too much something. So it's not going to be a simple choice. If we can already do it well classically, we'll keep doing it classically. If something's impossible today, but will be possible with quantum, okay, well, we can't compare the energy to anything. We're just maybe really happy we can do it.
How can quantum help AI accelerate?
Well, as I joked before, quantum computing companies would love some of that AI investment money, so they're all coming up with reasons how to do it. There are 3 ways where quantum and AI interact. So the first is using AI for quantum computing itself, right? So buried down deep. And here we want to think of AI, particularly machine learning, in a very simple form. It finds patterns. And then you have to decide what to do with the patterns that you found, right? Or instances of the pattern. Well, quantum computers, being quantum, and the universe being quantum, you and I being quantum, the universe wants to really mess up your computation. So there's a lot of noise that's introduced at the quantum layer, both classically and in the quantum interactions. We can use AI to better understand this noise, the problems that are introduced from the environment, and maybe subtract it. So imagine you're wearing noise-canceling headphones, right? Well, how does that work? Well, it understands the signal it's getting from the device or iPhone, whatever it may happen to be, but it's also listening to the environment, right? It's observing the patterns of noise from the environment, and it's subtracting it in some way. Okay, well, that's a nice AI application because you don't want to just strictly subtract it. It would sound very tinny. So understanding these things. So again, that's a simplified way of doing it, but machine learning has a lot of applications to making quantum computers just work better. Okay, well, now you got your quantum computer. Can it be used for AI? And people are examining new types of algorithms that we might use. As I mentioned, whether it's neural networks or anything, finding patterns. You cannot translate a traditional neural network and just pick it up and run it on a quantum computer. For example, in the very first step of a neural network, you copy all the information, right, that you have to start with to the second stage. Except in a quantum computer, you can't copy information. So the very first thing you would do, so you have to come up with completely alternative ways of doing this, right? So there are quantum versions, not strictly comparable. So people are exploring what we can do today to replace classical neural networks with, if you will, quantum computing analogs. And so those are useful. Maybe with quantum computing, different tools, we can see different patterns. But there's a gotcha. And if you're ever reading an article that says, oh, well, we're producing petabytes of data a day, thank goodness we have quantum computers that can quickly process this. Moving classical information, all those zeros and ones, into a quantum computer is exceptionally slow. The general case is exponentially slow. We today cannot move a lot of data into a quantum computer. You can't. The status of the computer just becomes garbage, chaos, right? So today you can't start with classical information as you might in a normal AI application. It has to be very special. So that will only be solved once we have error correction, fault tolerance coming in. And that will come in. It's starting to sneak in, but it'll be the early 2030s probably before it's being done at scale. So I started with AI for quantum. That was quantum for AI. And the next one is what I sometimes refer to as quantum and AI in the same general neighborhood. When we solve problems, there's not just like one computer. Send it to the one computer and it solves all the problems. There's a workflow. So it can run on many different processors at many different times. The data comes in and out at different points. And so some of those components within the workflow will be AI. Some will be quantum. There's an example of Microsoft, for example, working with the Pacific Northwest. And quantum helps produce better parameters that are fed into an AI model, right? So you use it what it's good for. It's not one or the other, but one can enrich how the other does its normal thing, if you will. And that's what we will see first. Just as I said, HPC and quantum will be combined. So that's within the same workflow, within the same general neighborhood, right? And those are the three use cases.
Can I ask a question?
Of course.
Yeah. So about quantum and AI, because you were saying at the moment, hey, why should we care about problems that we can actually solve within a classical computer in a reasonable time? How do you think about, what AI does now? Suddenly, the set of problems that we can solve with classical computers, like, expanding super, super quickly. We couldn't fold a single protein now, we're moving. How do you think about it, especially to your point with the timelines of quantum and how quick AI, like, which areas will be interesting or not interesting, or how do you think about that? Like, basically, AI expanding classical computers much faster to new areas.
So AI is in certain ways, sometimes they're heuristics, right? So it's not what we would call an algorithm. It's just giving an approximate answer to this. And people are doing that. They're trying to do hypothetical sorts of situations. With problems that are fundamentally combinatorial, and the classical one is the traveling salesperson problem. So I start in one city, and I'm given a list. Let's just say 50 cities. Right? And, I'm going to give you the distance between each city, and you have to compute the shortest path, starting in one city, going all through every other city, and ending up at the same one. AI is not going to help you with that. There are classical heuristics, but that is a problem that is well outside anything AI is going to do. Now, okay, as it turns out, quantums can't quite solve that either, but what it will be able to do is increase the threshold of how many cities, in this case, you can actually use, right? So quantum, there are certain types of problems. There are certain types of mathematical operations that, yes, AI does use, but it's this notion of very bad, exponentially bad combinatorial problems. You sometimes see these in risk analysis, financial services, and then chemistry, because chemistry is quantum. And so that's just, quantum tools for a quantum application. So they're not, it's universal, but there are a lot of things you'd never, ever use quantum for. You would never create this sort of video application using quantum. The overhead would be much too high to be anything practical.
What people are also very excited about in this intersection is synthetic data. Could you comment on that, Bob?
Well, in a couple of different ways. So the idea is to basically have a real data set and then have a much smaller data set that statistically represents what you're trying to do in different ways. You have to define this. Quantum may, in the long run, help you to do that. Interestingly enough, because you don't simply go from lots of data to the one synthetic data set, right? You have to say, what do you want of that? What are the statistical properties? What are the relationships that you're examining? Turns out that there's data preparation for use in quantum computing. So I think at the moment, it's not so much quantum computing helping to generate, in a very general way, synthetic data. It's understanding how to prepare classical data for best use in a quantum computer to get past some of these restrictions. And then, oh, by the way, if the data does have structure to it, some of these problems about loading it can be overcome. Whenever you have a very specific problem, you're going to do better than the general, in this, worst case, exponential situation. So that combination would be more useful.
It could also solve the problem of data scarcity, but there's privacy issues. We want to get to an era of data abundance, I think is what they call it in the AI world. Yariv?
Yeah, I think there's a bunch of interesting stuff in that domain in the AI world. I think the one interesting in terms of the data, the synthetic data, is still proteins. And again, it goes back to the chemistry. There is like 10 to the 100 possible proteins. We know like what, like, I don't know, a few millions. And if you look at how many antibodies, we know 5,000. And even still that is companies like AlphaFold and whatnot, actually doubling these few millions, and we need much more than double to get to 100 is very expensive. And companies actually, companies' Moats are actually being able to find good proteins to generate useful drugs. And I think like, yeah, right, like, if you have suddenly quantum that can do all of that at a much, much, much faster rate or more accurate. I don't know, like if it can do actually, can it do also like, super engineered? Because I think like what's the interesting thing that AI does is that in the first time, whether you operate on the geometry or whether you operate on the proteins, you can actually engineer drugs with certain properties. And there is still a receptor, right? So it's not just about being generate fast and at the quantum speed, very complex quantum systems. How much can you control it and how much can you define kind of a policy of requirements in a language that is understandable to us, but I don't know, like, I'm actually curious, like, that will it work for these cases where you want to engineer drugs with complex properties?
So just first of all, I don't think you should start by thinking of a quantum computer as any sort of big data machine, right? The amount of data, I mentioned petabytes before. In quantum, we talk about dozens or hundreds of data points, right? And the issue typically is not so much the data ingestion problem, it's the computational complexity once you're inside the quantum computer, right? So that we're examining all the possibilities, all the possible molecules that might have this property or whatever. But today there is, again, this problem. When the quantum computers we have today all use what are called physical qubits. And here we have to get into the terminology, right? But what it essentially means is we either use atoms, cesium or rubidium typically, trapped ions, so charged atoms, things like strontium, right, calcium, and so forth, photons, light, but we also manufacture some of these types of things. And when we try to use these in a quantum computer, they're only useful for a very short period of time. So if you read a book, for example, I wrote a quantum book. Boy, the qubits, they're perfect. You put information in them, you go away for 3 years, you come back, it's still there, right? But in a quantum computer, it's almost like, let's put the number 1.0 in a qubit in a quantum computer. And you come back in 5 minutes and you look at it and it says 0.99. And you come back an hour later and it says 0.9. And you come back in a day and it says 0, right? So there are all these things that are affecting the state of the actual quantum information that's in these computers. And they vary by how much time you have to do it. But also every time you do anything with this information, more errors are introduced in different ways. So yes, we try to make it as good as possible, but we're looking forward to, and much of the work today is getting, fixing these errors at least enough so we can do a lot of operations. So while chemistry is interesting, we don't yet have the scale for big enough problems. People have been looking at batteries as an example. particularly lithium sulfide, so lithium and sulfur. Can we use many fewer lithium atoms to get a battery of the same power? Lithium's a little element, right? If you look at the atomic structure, sulfur is a relatively little thing. Proteins, forget. I mean, just forget them for like years and years into the 2030s. They're much too big because lots of these problems, as I mentioned, become exponentially bad as they get bigger. Right? So by exponentially bad, I might mean every time you add an atom, it gets twice as bad. You add another one, it gets twice as bad. You add another. So for problems that are exponentially bad, we try to match the exponential goodness of quantum computing to somehow control that. And again, that's a simplification, but if we can do that, and the qubits aren't becoming chaotic, if we have error correction, right, and things like this, we will eventually get to a system that can do things. And then finally, if I may, there's this perception that everything in quantum computing will eventually do will just be close to instantaneous, right? There will be problems, like chemistry problems, eventually, 10 years from now, protein problems that run for weeks on a quantum computer. But that's okay, because they were impossible before, right? So we're almost in the prehistory stage of quantum computing. We're doing a lot of research. We're trying to see what we can do now. But this future world of scalable, fault tolerance, error corrected, that's the golden age. And that's the next.
And by the way, are people already building systems where you can go up and down seamlessly in the accuracy? Like basically, because many times I don't care. I want to look at the thermodynamics. I want to see the macro, Oh, now I want to get really actually, because I don't, the fact that I can do everything at the most quantum level doesn't mean I always want to do it at the quantum level. Doesn't mean I want to do it on everything. Maybe I want to sample some stuff at the quantum level, but I want to create that continuum of computation that I can go as deep and back and deep as back.
That would be the interplay with high performance computing, right? If you're doing these things within a quantum computer, again, oversimplifying, you need more qubits. You need more representation of the information that may lead to greater accuracy. There are algorithms, for example, that for every qubit you add, you get another decimal place, if you will. That's not quite because it's binary, but that's the idea. So you have to increase the power of the quantum computing to get greater accuracy, but it might be good enough for a classical computation that you would then feed in elsewhere in the overall algorithm.
Okay, then I would like to ask you, what are some of the companies that you think are doing particularly interesting work in this intersection of quantum and AI? And what are some of those things that they are doing that jumps out at you?
First, let me give you the size of the scale. I try to keep track of all the quantum computing companies, the qubit makers, if you will. Despite Google picking up Atlantic Quantum and D-Wave buying quantum circuits, right? So some of them are absorbed elsewhere. We now have, by my count, 89 quantum computing companies, right? And that certainly, opens up lots of questions about investments and SPACs and, the eventual fate of these. In terms of AI, IBM is doing a tremendous amount and has done a tremendous amount for years. When I spoke earlier about using machine learning to improve quantum computation, I left IBM 4 years ago, and they had been doing that for a couple of years beforehand. NVIDIA is doing a lot of interesting work in that regard. Microsoft is doing a lot of interesting work. Amazon itself, a little bit, but mostly you see other people using machines that sit on their cloud to do those things. There are a few AI startups that say they're doing quantum. It's not always obvious that they are. There's this term called quantum inspired, by the way, which I am not in love with. It's like, I wake up every morning quantum inspired, right? And what that means is, you kind of look at how a quantum computer with its structure would attack a problem, and you pick that up, and that gives you ideas about how to do a classical algorithm to do those things. So there is that kind of feedback in that way. I would say all of the companies, the Quantinuums, the IonQs, the ones that are public or about to go public, Inflection, so forth, they're all actively looking at quantum and AI in different ways. And, oh, by the way, they're not just looking at quantum and AI. Sometimes they're just looking at AI, right? Because it leads them in certain directions. So they see it more holistically.
Okay. Yariv?
Like I said, when we see quantum, we go away. We've seen a few that are doing quantum and security, right? Kind of starting preparing companies for what happens to all their security. Well, quantum computing arrived, and there is AI elements over there. And we've seen some what mentioned, but we always say, hey, I know a guy who has this amazing quantum fund in London. Let me give you his name. He really knows what he's doing. I don't.
The security issue, is interesting. So any new technology that comes along, any powerful new technology, people ask about the ethics. And so there's been a huge thing about, for example, going on for years about bias in AI, right? All these issues, because it's so data oriented. So people always say, but what if the bad guys get this? What are the terrible things they're going to do? And you can always say, well, bad guys have very powerful computers. They're going to do the things that bad guys do, right? And a lot of people say, so we better stop right now, right? And people try to put up guardrails and things like this. The one thing with quantum that has persisted is this notion of breaking certain asymmetric security schemes like RSA or elliptic curve cryptography eventually. These go back to Shor's algorithm, 1995, which can do exponentially better factoring jobs once they're big enough to do this. And if you can do that, you can, in theory, get the keys, recover keys from elliptic curve or RSA. So in this regard, the cryptographic aspect isn't quantum. It's quantum is the threat. Right? So you really should pick yourself up and go over into cybersecurity, where you're always asking, what are the threats and what are we going to do about them? Right? And so in the United States, NIST, through an international effort, standardize new cryptographic methods that we believe, we can't prove, but we believe are not able to be attacked by quantum computers. There are other aspects of quantum security and quantum communications and things like this. So they're often blended, right? So post-quantum cryptography and things like this with quantum computer itself. But you don't need a quantum computer to protect a traditional computer in this way.
I also wanted to ask you about talent to work in this space. I mean, there's a scarcity in quantum in general. Where are the people that can bridge these two communities?
It's an interesting issue for the following reason. Yes. So I mentioned that there are 89 companies, hardware companies, that do this. That's a lot of companies that need talent. Mm-hmm. So first of all, if I were to have said there are 45 quantum companies, if I were to say that to a general audience, they would have said, that's a lot of quantum companies. Right? So, why do we need so many quantum companies? And by the way, why are so many of them going public? Which is another question. So if I were to just give you half the number of the actual companies, you'd still think it was large. So we have a fundamental dilution problem in the workforce. If suddenly overnight, half of the existing quantum hardware companies didn't exist, well, all those engineers and scientists of the different flavors of physics could pick up and move over, and people would probably stop complaining about workforce, right? Now, that said, in certain types of physics areas, yes, there is definitely a shortage in these companies. So AMO, which is atomic, molecular, and optical physicists, are in extremely short supply. And so lots of companies would love to get them in particular. Some of the engineering aspects are also. Now that starts to intersect, by the way, not all of the quantum modalities, as we call them, like the superconducting, like the IBMs, but some of the others, use photonics extensively.
Yep.
So light, basically, in different ways. There are many hundreds of photonics companies that are out there, many startups doing things that relate to quantum. I see for them, it's not so much a shortage of talent, but the talent's just not in the right place yet. The talent is in general photonics companies, and they haven't shifted into the quantum engineering aspect. So all in all, I think it's distribution and dilution with some particular shortages.
But by the way, do you think that in the near-ish future, they'll manage to create an AI agent that could be as good as a quantum scientist, at least in some areas, where maybe the lab is a bit easier to also automate, that will actually scale this research and be able to actually accelerate or commoditize the quantum researchers? I don't know.
Well, I think if you, so if we're asked a little bit more generally, can we use AI to improve manufacturing yield? Because an IBM or Google, whoever, they make chips. Ultimately, they have to make chips. And can we, so we can ask that. Can we do better than human intervention? A number of people are already using AI to create better processors, right? In the case of certain of these, you've got these qubits, which are in very particular places on chips. Well, what's the design? How are they laid out? Some, but not all, are connected to each other. Which ones? Right? Okay, well, that's a hard problem, right? How do you control these things? If I send a little microwave signal down to one qubit, it affects one nearby. How do I minimize that? Can I use AI to control the sequence of pulses and the layout, right, of the actual running application or circuit? So yes, in that way. And I would say it's not a person replacement situation. It's we're never going to get through that layer of complexity to optimize the design without AI.
Bob and Yariv, thank you very much for sharing your insights. I thought it was a very interesting conversation. I wish we could continue, but unfortunately that's not possible. So thank you again and hope to talk to you again soon.
Thank you.
My pleasure.
I learned a lot. Thank you.
Yeah, thank you very much. No, it would be nice to keep talking. There's a lot to be learned if you put two experts together.
No, it was fascinating. Thank you for inviting me.
Great insights. Thank you so much.